All right, guys. So I know I was gone for a big chunk of this unit, so there's a few things I want to walk through with you just to make sure you have it down for your quiz this week. So I'm going to go through kind of quickly, but you have all of this information in your green notes and in your textbook. First thing I want to go over is just a real basic definition of a wave, and that's going to be any disturbance that transfers energy from place to place. So anytime you're sending energy from one place to another. So it could be the sound of a bell moving through the medium, which is the air, towards our ear. We're sending the energy from the bell to your ear. Um, Waves need something to travel through, and a medium is going to be what it travels through. So a medium could be the air, a medium could be water, a medium could be a solid like a table. Waves always move energy away from the source by vibrating those particles of a medium. Mechanical waves are the kind of waves that have to have a medium. Um, Make sure you remember that, but that medium can be any substance, solid, liquid, or gas. Um, Sound waves always move fastest through solids, then through liquids, then through gases. Um, so, for example, sound waves speed up as they move through the air to the solid part of your eardrum, and seismic waves slow down as they move from a solid to a liquid. So, in our earthquake example, our seismic wave example, as they move from the solid rock of our plates into ocean waters, they would actually slow down. You guys did an activity, hopefully, while I was gone, with some coat hangers that had some strings tied to them, and then you hit the coat hanger on the side of the table and it made that crazy noise in your ears. Well, that was the sound traveling faster through the solids, through the hanger and the strings, than through the gas, which was air. We talked about types of mechanical waves. There's three types. There's transverse waves, longitudinal waves, and then there's also surface waves. Um, Transverse waves we focus on quite a bit. Um, these waves are going to vibrate a medium at a right angle or perpendicular to the direction in which the wave travels. Um, so this is our right angle here, okay? So if you drew a line straight down from the wave and a line across rest position, you should always see your right angle there. Um, Transverse waves are going to have clear crests and troughs, so high points and low points that are on either side of your rest position. We'll talk more about those here shortly. So here, if you are the source of energy, okay, and you guys did an activity with a jump rope where you were the source of energy moving the rope, energy would be moving away from you, okay, and then our medium, okay, is going to be the air and the jump rope, right? Um, so the energy is actually going to be traveling through the jump rope from you to the other side of the jump rope, okay? But you can see how our medium, the jump rope, is moving back and forth at a perpendicular or right angle to the way that the energy is moving, okay? One way to remember this perpendicular or right angle is I turn that T for transverse into my right angle, okay? So in a transverse wave, particles in the medium can move up and down or side to side. Okay, so here's just some more examples, some pictures of jump ropes. So in our transverse wave, the crest is going to be the highest point of the wave. So that's going to be this right here. You have to hit the very, very top. Okay, you need to be careful when you're identifying these things because if you're off just a little bit, it's not going to be the right point. And a lot of you saw that happen on your wave diagrams that you turned in. They were counted incorrect if the crest was not at the very top. Rest position is this bar right through the middle. The wave has no energy at that point. And then the lowest point of the wave is the trough. Again, just like the crest, you have to make sure to label it exactly at the bottom. Our amplitude is our wave height. So the distance from this bar at rest position all the way up to the top of the crest, or from rest position all the way down to the bottom of the trough. Okay, so this area can be going down or it can be going up. This is where we would measure our amplitude or the wave height. If you have a larger amplitude in your wave, you're going to have more energy. So in this picture, the first wave has very small crests and troughs away from rest position, that one has the least energy. And when we get these big waves, this one has more energy. Think about the jump rope. If you don't move it very much, if you don't apply very much energy, it's not going to move very far. But if you're really moving the jump rope, adding a lot of energy, it's going to look like this. The other thing that you looked at was wavelength, and I think a lot of people had trouble identifying this one. But this can be in a transverse wave, it can be from rest to rest, crest to crest, or trough to trough, and I'll identify those on a picture for you in just a second. In a longitudinal wave, it's the distance from a compression to compression or rarefaction to rarefaction. Okay. The shorter the wavelength in a wave, the more energy it has. Okay, it's just all pressed together, concentrated energy. And then our frequency is going to be the number of waves that passes a certain point in a certain amount of time. Okay, so if one wave passes by every second, then your frequency is 1 hertz, because our units that we use for frequency are hertz or Hz. If 2 waves go by you every second, then it'd be 2 hertz. So for example, if this is a 1 second time period here, if we go 1, 2, 3, our frequency here would be 3 hertz. Okay, our frequency would be 3 hertz. Again, higher frequency equals more energy, because you're having more waves pass by you in that time period. There's more energy behind it. We talked amplitude. Longitudinal waves look a little bit different than our transverse waves. Here the particles are just moving back and forth. They're not moving side to side. And our big example of longitudinal waves is, of course, sound waves. We have the vibration coming from our speaker here. And we have our different, let's see, this is labeled as a rarefaction, and then compression is where they're pressed really close together. Okay, so a wavelength again would be from this compression to this compression is 1 wavelength. You can see here there was a write-in in your book, figure 3. Compression is this area pressed together. Rarefaction is this area here. You guys probably demonstrated this with slinkies, moving them straight back and forth. So just forwards and backwards is a longitudinal wave. If you move it side to side, it's a transverse wave. But make sure you can identify these areas. We have our rarefaction, compression, rarefaction. Okay, so if this was a 1 second time period, this would actually be 1.5 hertz. The top picture would be 1 hertz, because there's 1 compression and 1 rarefaction. Okay. So our compression is where they're crowded together. Rarefaction, where they're spread apart. Try to do some examples on your own. So draw a longitudinal wave with a frequency of 3, first of all. Okay, and I'm going to shrink this up. So a frequency of 3, we'll see if I can do this with a pen here. So if this is the start of my interval, here's the end of my interval. This is going to be messy, I apologize. We need to have 3 wavelengths go by in this time period. Okay, so if this is a longitudinal wave, then 1 wavelength is 1 compression and 1 rarefaction, right? I'm going to start with a compression. Ooh, this is going to be bad. Okay, and then here's my rarefaction. See how they're more spread out. And then here's my second compression. They're going to be closer together. I had 4 in my compression. And then my rarefaction, they're more spread out. Okay, and here's my next compression. And then in my rarefaction, I'll put one over here, they're more spread out. Okay, so this would be 1 wavelength. Okay, and then compression to compression is 2 wavelengths. Compression to the end of this rarefaction, this would be 3 wavelengths. Okay, so this is a longitudinal wave with a frequency of 3, because I have compression, rarefaction, compression, rarefaction, compression, rarefaction. Okay, so give yourself some time to practice those. Another example, a transverse wave with a frequency of 3. Okay, so this is my rest position. Okay. So this is one wavelength. Okay, you go to where the wave starts over in the same position. 2, 3. So I would have to stop right there. If I go any further, then my frequency is not 3. Okay, so make sure if you started here and you go up and do a crest first, the same place on the next wave would be a different wavelength. So we start here, go up. So I like to count this way. So I start in my first position, and I go up, down 1, up, down 2, up, down 3. Okay. Now another way you could have done this get my pen back, is you could have started up here at a crest, okay? And that's perfectly fine. Just make sure you go to the next spot on the next wave. So if you started the crest at the top, the way you would count this is from crest to crest. So I'd go all the way down and all the way up 1, all the way down and all the way up 2, all the way down, and make sure you go all the way up again for 3. Okay, you have to go all the way back to the same spot on the next wave. Okay, the third place you could have started this okay, is down here at the trough. Okay, so bottom 1, bottom to top 2, make sure you stop at the bottom, and then back up to back down is 3, but I have to stop in the same spot. Okay, so trough to trough is 1, trough to trough is 2, trough to trough is 3. Okay, a lot of people had problems counting wavelengths. If you still need help with that, please come see me. It's really important that you're able to do that. So these are just some other practice. Another thing you talked about is resonance. And this is an increase in the amplitude, so how far it moves from rest position, of a vibration that occurs when external vibrations match an object's natural frequency. So this is a pretty complicated definition, but basically when two things are vibrating at the same frequency, one of them, the amplitude is going to increase. And you guys saw examples of this, you guys saw examples of this in a video with the opera singer. Shattering the glass, and Miss G tried to make the glass make noise for you. You guys all went into her classroom the other day. You can also do this with tuning forks, but I don't know if they did that demonstration for you or not. Okay, so basically resonance, when two objects vibrate at the same frequency, one object causes the other one to vibrate more. Sound itself, oops, now I need to get rid of my pen. Sound is a disturbance of energy that travels through medium as a longitudinal wave. I'd mentioned that to you earlier. So that wave is always going to have the compressions and rarefactions. Sound is not traveling as the transverse wave that you see in the bottom here. Let's see. So sound waves, in your book you talked about how sound waves travel. Just remember that they're always going to move away from the source. And that they have to have a medium to travel. Okay, so they're traveling through air, they're traveling through water, they can be traveling through solids. This is why you cannot hear sounds in space, because sound waves have to have a medium to travel. So without air to travel through, the sound waves can't travel anywhere. Pitch, pitch you started talking about just when I got back. And pitch is going to be how high or low the sound sounds to a person. Okay, so this is going to be based on who's listening, but this is all dependent on the frequency of the sound wave. If you increase the frequency, so the number of waves that are passing you per second, for instance, if you increase that frequency, then the pitch is going to sound higher. If you slow the waves down, if you decrease the frequency, then you're going to have a lower pitch. We did this in class with this fill-in. The female opera singer has the higher pitch, and so she has a higher frequency. You see more waves passing in the same amount of time. And then the male singer has fewer waves passing by, so he has a much lower pitch because of his lower frequency. So again, the pitch is going to depend on the frequency of a sound wave. Please make sure you know that a higher frequency is a higher pitch and a lower frequency is a lower pitch. Loudness is going to be how we describe the energy and intensity of a sound wave. So if a sound wave has a lot of energy, then it's going to be very loud, or if it's very intense, it's going to be loud. Okay. Intensity is the amount of energy the wave is going to carry per second through the area. We talked about intensity as sitting in the front row at a concert here is the most intense. You're closest to the stage. If you're sitting in the back, it's less intense. There's been more space for that sound wave to spread out, so it's less concentrated. We also talked about like the Mio drops. They're really concentrated right out of the bottle, but the more they spread out, the less concentrated they are. Sound waves kind of do that same thing. So in your green notes, I have loudness describes how aware you are of the energy of a sound wave, and the greater the energy, the louder the sound. Okay. The units we use to measure loudness are decibels. You guys did some decibel research projects. Just remember that this is a logarithmic scale. Okay. So a 10 decibel sound is 10 times more intense than 0 decibels. A 20 decibel sound is 10 times 10, so it's 100 times more intense than 0 decibels. And a 30 decibel sound is 10 times 10 times 10, 3 tens, so it's 1,000 times more intense than a 0 decibel sound. So remember, some people were remembering 30 decibels as 3 zeros, so when they did 1,000, it's 1 and 3 zeros. And then the other thing I want to remind you of, a 0 decibel sound is not silent. It's just the lowest sound of the human threshold, okay? Sounds louder than 100 decibels can damage our ears. So make sure if you are experiencing sounds that are that loud, you're wearing ear protection or you're limiting that exposure. And then the last thing we talked about was the Doppler effect. This is the one with the video clip from Big Bang Theory. Okay. The Doppler effect occurs because motion of the source causes waves to get closer together or spread out. Okay. All that means with our fire truck example is that as the sound is leaving this fire truck, some sound waves are going behind it and some are going in front of it. Okay. They're all spreading out from the source, which is this speaker on top of the fire truck. So the ones in front of it, the fire truck is moving towards them. So they're getting smushed together, which is increasing the frequency. And you'll remember, if you increase the frequency, what happens to the pitch? The pitch is increasing. So in front of the fire truck, where the frequency is greater, the pitch is greater. Behind the fire truck, they're moving away from the waves, so they're more spread out. So the frequency is lower and the pitch is lower. So when the fire truck goes past you, before it passes you, it's a higher sound, and then after it goes by you, it's a lower sound. Okay. Then the very last thing we talked about was just how your headphones work and how sound travels through. So if you just take a look at that in your textbook on page 45. So hopefully going through some of this, I know it was quick, I apologize, but going through some of this will give you an idea of what you are expected to know for the quiz. If you have any questions on any of the material, please just stop by and see me.